Okie dokie. So in this screencast, a couple more examples of volumes by known cross sections, focusing on shapes this time that are not squares or rectangles, nice, easy shapes. I want to do a couple of examples with some weirder shapes where the geometry is a little more complicated, but the calculus is essentially the same. So I have set this up already. The base of a solid is the region bounded by what? Oh, that should be blue. Y equals 1 minus x over 2. That's the blue line. Y equals x over 2 minus 1. That's the red line. And the y-axis, that's this line. Cross sections perpendicular to the x-axis are equilateral triangles with one side in the xy plane. So this is an equilateral triangle, this is an equilateral triangle, this is an equilateral triangle. So we take a slice cross section perpendicular to the x-axis. So we slice perpendicular to the x-axis, perpendicular to the x-axis, and the shape that sticks up from that off the table is an equilateral triangle. Each of these are just Doritos. That's all they are. These are just Doritos. So the question is, what is the volume of a Dorito? Well, it's the area of an equilateral triangle times the thickness, right? I mean, the thickness we sort of know is going to be a delta x. But this area is the area of an equilateral triangle, and this may or may not be familiar to you from your high school experience, but the area of an equilateral triangle is side squared times radical 3 over 4. We can prove that. It's not very important to the question, and it really is more high school geometry than calculus 2. So the area of an equilateral triangle is side squared radical 3 over 4. So in our case, what is the side squared? Well, the side runs from the blue to the red. The side runs from the blue to the red. So how long is that? Well, it's this minus that. And a little bit of algebra indicates that that's 2 minus x. And that's true for this Dorito or this Dorito or this Dorito. All the Doritos are the same. So the volume of the Dorito loaf is an integral of side squared radical 3 over 4 dx. From where to where? Well, it appears 0 to 2. The y-axis is on the left side, and then these two lines intersect when x is 2. So that ends the interval of integration. How do we do this integral? Well, the radical 3 over 4 comes right out because it's a constant multiple. And I passed algebra 2, so that's that. And then we take an antiderivative, sub, and subtract. I'll try to be tidy. We take an antiderivative, one term at a time. We substitute the 2 and then the 0, which is substantively easier, and we subtract. And this turns out to be 2/3 times the square root of 3. A very guessable answer. You probably had that already. So the only thing that's different from the examples in the last screencast and this right here is the geometry of an equilateral triangle. It's still volume of a slice, add up all the slices, a little bit of algebra, fundamental theorem, and we're done. That's the big difference. I'll demonstrate with one more. The base of a solid is the region bounded by sine x and negative sine x. The blue one is sine x, the red one is negative sine x. Cross sections perpendicular to the x-axis are semicircles whose diameters connect the graphs. So This is half a Ritz cracker. This is half a Ritz cracker. This is half a Ritz cracker, right? So we get this Ritz loaf. It's got a flat side on the table, and it's of varying heights coming off the table depending on what this is. So what's the volume of half a Ritz cracker? Half a Ritz cracker. So the volume of half a Ritz cracker is pi over 2 radius squared, right? Because a whole circle would be pi r squared, but we only have half a circle, so it's a half of pi r squared. And then there's a thickness to consider. We're cross-sectioning perpendicular to the x-axis, so this thickness is a change in x. The question is, what's the radius of this half a Ritz cracker? Well, the radius of half a Ritz cracker appears to be from the x-axis up to the blue curve. From the x-axis up to the blue curve, that's sine x. And that's true whether we're dealing with this cracker or this cracker or this cracker. It doesn't matter what half a Ritz cracker we're dealing with. We're dealing with half a Ritz cracker. And these are all the same. So we integrate. It's an integral of pi over 2 times sine x squared dx from where to where? Well, that looks like it's 0. This is the next place the sine curve hits the axis, and I'm pretty sure that's pi. Now, we have not yet studied how to do this integral by hand, and so we use technology to figure out that this is approximately 2.467. And in my course, because I am a long-time trained AP instructor, we do everything to 3 decimal places. Again, the process is the same. We find the volume of a slice. We recognize that all the slices are roughly equivalent. We take a Riemann sum and turn it into an integral. And then we use our abilities to figure out what that volume is. So the only thing that's different here is the geometry. Hopefully this lays down a decent foundation for you. Hopefully it supplements what you've been reading. And hopefully you will engage in some of the practice questions so that you know how this thing works when you actually sit down to do it. Looking forward to seeing you when we gather. All the best until then.